All right, guys, welcome back. Hope you had loads of coffee to keep you awake. I know we had another hour and a half. I might skip over a couple of notebooks because I want to get to some of the important ones. So let's go to our third one. Let's go to our third pattern called actors. As I said, actors are quite important, quite pivotal in Ray because it allows you to write stateful applications. Actors are heavily and prominently used in Ray native libraries. Actors are used in data sets, in Ray train. You can actually use actors. You can use pool of actors to do things. And one of the great things about those actors is that just using the APIs, you can actually make remote calls and send messages back and forth without actually, figuring out or worrying about or reasoning about how you're going to, who you're going to connect to, where it's going to connect to. So when you instantiate an actor, what happens is that the Raylet schedules an actor on a Ray worker, right? And the Ray worker now becomes an actor, right? So it used to be a Python worker, but there's a dedicated actor worker to a Ray. So when a Ray actor is scheduled, for example, this counter, it gets shipped over to the worker, and now the worker the actor actually takes over. So this entire worker node with all the cores is dedicated to this particular actor. When the actor dies, it just becomes a worker again, and then it moves on. So let's look at what it actually looks like in terms of programming. It's quite simple. You can take any class that you actually have, that you have methods in it that you keep a particular state, and by just annotating that with the ray.remote, now we have converted that actor into a remote setting. So we're going to go ahead and import some stuff over here, and we'll go through the same exercise to figure out whether it's initialized or not. Get the web URL. So that's my dashboard. And what we're going to look at is an example of a parameter server. And those of you who are doing deep learning, or those of you actually doing distributed programming, a parameter server is an important tool or important element in computing gradients of all these workers which are actually sort of running a remote task. So pictorially, you can think of it, a parameter server is a server that actually keeps state of all the weights. And these worker nodes are the ones that actually compute the gradient. So you want to keep track of all these gradients and then report back to the parameter server. So that's sort of the architecture where the parameter server has a bunch of worker nodes. The worker nodes are computing these gradients, and they're reporting back to the parameter server. How do you actually implement that, right? Now, you could write C++ code, or you can write Python code, in which you actually have to worry about the interprocess communication, you have to worry about all the network traffic and serializing and deserializing. This, you can actually see, you can do it quite easily. A lot of other code I've taken it out, but I'm just trying to illustrate how easy it is for you to do that using remote actors. So what we'll do is we'll create a class called class parameter. I'm just going to initialize our gradients to be 0, just for the sake of exercise. And then I have two function calls, or two private methods, or public methods rather. One is called getParams, which just returns the current parameters we actually have, the current state of the parameter server. And then update parameter just updates the gradients on the parameter server, right? Something very typical that what distributed workers actually do. So this is my remote class. I do that. Now I'm going to define a worker. Again, I want to distribute that worker as a class. As a function, so we're going to go ahead and create that as a remote function. And all I'm going to do is I'm going to iterate over a number of epochs, and I'm going to compute the gradients. This is kind of superficial, but you get the point, right? This is actually what happens when you are training, say, in XGBoot. You write a trainer, you write an objective function. Your objective function is going to iterate over epochs. You're going to compute the loss. You do the gradient computation, and then you keep on going. So this is somehow simulating a worker doing this. So over a number of iterations, over a number of epoch, I'm going to sleep for a while. We're actually computing the gradients. I'll update the gradients, and I'm going to now invoke the parameter server, which is actually now been passed as an argument. Let the subtlety over here. The argument over here for the worker is a parameter server. And we'll look at how that actually works. So this parameter server is actually a handle to the parameter server class. And over here, I'm just updating the gradients by just sending this particular gradient that I've computed over here. And this is going to be a remote call to the parameter server to update that. Very simple, right? In real life, you would actually have to make an RPC call. You have a connection handler, all these different things. This is all taken care of you very easily. So this is a good way to sort of distribute a task using a worker. So you got a parameter server, you got a worker, worker's computing gradients, it uploads to the parameters after each epoch. Very typical thing what you actually do in training. All right, so now we're going to create a parameter instance server, which is very simple. All you do is take the class and then create a remote, and that returns you a class handle or parameter server. That's an instance of a parameter server. If you print it out, you will see that this is of type actor, and it has some reference. What does that mean? It means that this particular reference is where the code is going to be serialized on the GCS where the actor is actually running. Oh, I mean where the code is residing. So the first thing we actually do, just to see what the parameters are, we'll just do an initial print parameters using typical get parameters.remote, and we do that. And then it's just doing a get. Initially value obviously is going to be 0 because none of the workers are working. Now let's go ahead and create the workers. And the workers over here, I'm just going to create in a comprehension list, but I'm not going to store them anywhere. So this is my list of workers to which I'm actually sending the parameter server for range from 1 to 3. So I'm going to creating 3 workers. Very simple. That just returns me an object references. And then what we're going to do is for 20 iterations, we're going to go ahead and send the parameter server and update those gradients, sleep for a while, and iterate over the loop. Right? So this is what's happening. Now the workers are running, they've been launched, and each worker now is going to go through its epoch, and it's actually updating the parameter server. Just a few lines of code, we can actually do this using actors and using remote workers, right? You can think of this can be sort of implemented as an orchestrator, which is a parameter server, an orchestrator, which actually has a worker. Each worker has your objecting function. Each objecting function, it could be some gradient that you're actually computing over a period of epochs that you have, and updates the gradients and then reports back to the parameter server. If you look at some of the old code like Horoward and all the parameter servers, that's pretty much how they implement it. But if you look at the C++ code and all that, there's a lot of code involved over here. But you can actually see this is done very, very easily, right? Just using the remote methods. The third pattern, which is part of the actor pattern, is called tree of actors. And tree of actors is very much used in all the libraries. So RayTune, for example, uses tree of actors to create a runner, and the runner actually has all these workers, and the workers are getting each and every slice of your config space to do your trial, right? So if you're doing grid search, if you're doing parameter search, if you're doing distributed search, each of those workers actually get a slice of it. It computes the loss and then reports back to the scheduler or the orchestrator, and the orchestrator supervisor says, "I'm going to create a new trial. I'm going to send it to the trainer." He will do that. So this particular pattern, which you actually see that happening throughout some of the native libraries that we actually use. So over here we have a trio actor. We have a supervisor. This is very similar to the parameter server we actually created. We have a worker actor that's going to do your job, and the worker actor now reports back to the supervisor what my state is, and the driver is the one who actually just is the supervisor. So just to give you an illustration as an exercise how simple and intuitive to give you the intuition of how easy it is to actually write this, is that we're going to maintain some states, right? We're going to running state, pending, and done. And we have a model that we're actually training, right? Initially, we're going to initialize the model in this particular class, and then we'll have a train function in that method. Go ahead and train that. And normally over a train, you probably have an objective function that goes over a bunch of parameters, a bunch of training parameters, and trains it, and then returns back the results, right? And we're gonna have a factory function that says go ahead and create 3 models. Now, normally when you're doing when you're constructing or creating models or solving business problem, you're not going to create just one kind of model. You might have different kinds of model, because the whole idea behind creating models is that you actually want to use A, the best library, B, the best model with the best parameters, and C, you want the best metric that one of the models actually meets. So over here, we're just going to create a factory. We're sending in, go ahead and create a logistic regression, or go ahead and create a Scikit-learn creation, or go ahead and create an SVM, and that's just going to create a particular model and return you the instance of that particular model, right? This is all skeleton code, but this is how you would actually write training in distributed manner if you actually had to. And now we're going to create each worker. Now each worker is actually a class again that gets one of the models. I could actually have a regression model, or I could have a classification model, or I could have a neural net. Doesn't really matter, right? Each will have its own function to train that. We initialize that with the model. We actually have a state that returns you any one of the random choices. Over here, obviously, you will have logic that determines where you are in the training cycle. But over here, I'm just returning a random choice. And then the worker is the one that actually creates a particular factory and says, OK, I'm going to go ahead and now invoke the model called train. So that's the skeletal part of it. And now we're going to create a supervisor, right? Supervisor is the big one. And that will have a local state that maintains all these 3 models that I'm creating, right? So for each type of model, I'm going to create a particular model, and I'm going to send that model to the worker. So the worker now has a state of that model. And so these are all my workers, right? This particular is the function which is actually the workhorse that says go ahead and do the work. And the way I'm doing it is just comprehension, right? For each worker, go ahead and invoke his remote class to do the training. And then terminate is just go ahead and terminate that particular model when I'm done with it. And the state is just one that just returns you the current state of the workers. Very Pythonic code, right? Very, very, very simple, very illustrative, very intuitive, right? If you have low comprehensions, if you love Python, you can just write this code very easily in Python, and all this is actually happening underneath for you in a very distributed manner. Okay, so let's go ahead and create a remote supervisor that returns that. Now let's look at my dashboard. If I go to my dashboard, go to the logical view. I haven't launched the actors yet, sorry. So here, this is my main loop that's actually going through each and every state that's printing it out, right? So it's doing the worker, it's computing the state, and when it's actually done, it updates the particular state, and when all the state is actually done, I'm pretty much done with that. Now what I'm done is actually I'm passing all these actors to the handle, right? You can actually see, just like in the parameter server, you actually sent the entire parameter server. Over here, the supervisor is getting the workers, and it's actually working on the workers. Okay, all my actors are gone. Otherwise, you could have seen that in the dashboard. Let me kill this. Whoops. So you can see I have my parameter server running. Right? If I go my logical view, this is where all the actors are. So here's my parameter server that was running. Here's my supervisor as an actor. And here are all the workers, right? If I look at beneath that, I'll see what's being executed, at what time. You hover over it, actually tell you how many tasks is actually executed. The supervisor has one supervisor which is still alive. I have a worker, just finished all the tasks that the worker finished. I have that. So this is sort of a good way for you to look at the dashboard and see how the worker is actually created, right? So when you are running and when you're debugging, supervisor is a good, dashboard is a good way to say what actors are running, what number of execution tasks they've done. When you have a long-running actor that actually doing a lot of training, you actually see these things actually updating in real time. So what I've done over here is using this particular parameter server example to implement what we call a tree actor pattern. So this is my supervisor that has 4 workers or 3 workers, and I've just simulated a model training in a distributed manner. I've created a worker that actually has a model that keeps the state of that particular model as it goes through all these different choices. I have 3 models running in parallel. Supervisor is the orchestrator that's maintaining the state of which model has done training, and once they're done, I can actually kill them at a time. And the way you actually create a supervisor is very simple. You just take the class, create an instance, and once you invoke supervisor work.remote, everything starts just percolating, starts running in a distributed manner. And then this is just a loop that actually does that. You don't really have to kill and terminate actors explicitly. When you do a ray.shutdown, it automatically kills all the actors and cleans up the object store. But there is a way you can actually kill it for some reason, right? If you just wanted to be more control freak, you can actually do that. Any questions? I think this particular pattern is very important because you're going to be using that in quite a bit, right? Especially if you're doing training. If you're writing distributed application, if you're using ray tune and ray train and ray datasets, all that is actually taken care of here. You won't be actually using ray put and ray get and orchestrating all that is taken care of you. You just use the API, say, here's my tune function. We look at one function, we look at one a notebook. Here's my objective function. Here's my search space that I actually want to search over. And here's my epochs I want to run and go and run in a distributed manner, right? So on my local machine, I'll create all these trainers that will actually run. In my distributed machine, it will actually go across my AWS cluster or my GCP cluster and run those hyperparameter tuning remotely. Any question? Yeah. Yeah. So if you what you're actually sending is just you're just sending a handle to the parameter server, right? And if the parameter server is taking any particular input and those input reside on a plasma store, if they're on the same machine where the worker and the worker is running, then it will just use a plasma store. But if it's not, and the weights are very small, so it just uses straight gRPC soup call, do that. So the good thing about Actor is that Actor run in their own process, right? So if they're running in their own process and you're executing the methods are executed serially. That's one of the reasons that you will never have 2 same instances of Actor running there. They can run on a separate process, right? But when you call the particular method, you won't have the race condition because now over here the methods are called serially, right? They're not called asynchronously. Otherwise, you're going to run into race conditions, right? That's why we actually made a design choice that when you do an actor, the actor is going to be consigned to one particular worker that's going to take that over, and you're going to run all the methods for that actor. If you create another instance of the actor, which is now a different reference, you will get a different worker for it. Right? It will never. 2 actors of the same instance won't be allocated on the same worker. On the same worker, you will be a different worker node, but they'll be running separate instances. Answer your question? Yeah. Mm-hmm. Yeah, that's actually a very salient point because otherwise, you run into that issue. Any other questions? So this is another class which is kind of a little more in-depth. that deals with, no, actually, we went through the message. This is done, yeah. So here now, I have a message actor that's getting messages from different workers. This message could be anything, right? It could be a little publish-subject diagram. It could be a state of something. And I'm just appending as messages coming on a particular queue. And then I have another method called get and clear messages that just initializes a message. So if you wanted to write a message board, this is very easy to actually do that. So we create a message actor with initial messages as an empty list. Append just appends to the list that another worker actually sends it. Reset and clear, very simple, illustrative of that. And then I have a remote worker that sends the messages to it, and the remote worker now sends the message actor, gets the message actor as an argument, so you can actually send a message to that based on whatever message we actually want. So this particular function is a remote task that's going to be scheduled. And we create a message actor. We start 3 tasks over here. And we just iterate over a bunch of messages. So now these messages are getting updated, right? We're running. And when we're done over the loop, we will be pretty much done, right? Now, normally this is something that's actually running indefinitely. So as soon as it actually gets an update, the message queue gets updated with the appropriate message. Now, these are toy examples, but I think it gives you the intuition of how seamlessly you can actually use actor and methods to actually write distributed pattern, and how easily you can actually use these 3 patterns to use actors in that particular manner without worrying about where this particular method is going to execute. How do I have to worry about sending messages to it? How do I worry about scheduling it? All that is actually done for you automatically. And then finally, we do a rest shutdown, and all those actors should disappear. Any question? Now, there's an interesting exercise here. I really want you guys to have a go at it. I have a solution for you, but this is pretty much based on the messaging class. Think of it this as a logging actor that remote trainers or remote actors are just logging to it, right? So you have a distributed logger that allows you to be able to keep track of all the logs. So take a look at it. There's a solution in there if you want to take to it. If you don't want to do it, we can move on. How many want to do the exercise? Okay. You're a minority, mate. Okay, I'll give you 5 minutes. Is that too much? No. All right. So try to do it at home. You should be able to do it. The solution is there in the solutions directory. There's just a couple of lines of code you actually change, but the framework is there. I've already given you the framework. You just have to do a get of this in a slightly different manner. But everything else is there for you. So this particular skeleton is there. You just have to do a couple of other things. Like, for example, here, to do, this is what you actually have to change. Okay, some references. These are actually good, couple of good blogs that I think this is the one I wrote. This is Advanced Patterns and Anti-Patterns is a good way to figure out what's the right way to do things. These are patterns which we recommend that when you're writing distributed application, use these particular patterns. They're also anti-patterns, right? So, for example, the way you actually do get, you never do a get in a loop. It's one anti-pattern. Remind me, if you look at all our gets were done outside the loop, because what happens is you're going to get block on every get, right? So we do a get on the outside. We get the references, the list. We build the list either comprehension or appending outside, and then we do one big get, which then returns your list. Yes, my friend.
That bottom link, advanced patterns and anti-patterns in red.
Yeah. Is it? Thank you. We went through a revamp of documentation, and I bet that got disappeared. But thanks a lot. Yeah, I'll fix it, and I'll do a pull request. I'll fix it tonight. Just do a git pull tonight, and you'll be fine. Maybe after lunch we'll do that. Okay, so these the next two notebooks are kind of read-only, so it'd be sort of boring for me to just talk about it. But I just wanted to give you a quick overview of what these two notebooks are. There's no exercise associated. This sort of gives you a more in-depth of what are the things that you can supply to init. For example, if I wanted to talk to a remote cluster over here, I'm just doing ray.init, and by default, it's going to talk to the cluster. Well, ray.init, there's no cluster running locally. It's going to go ahead and launch one, right? One head node, and then now you actually have a ray cluster. I could actually say something like ray.init auto address is equal to auto, and what that will do is that it will look at the environment variable to see what head node should actually connect to, right? So if I already have a ray cluster running by typing locally ray start.head, it's going to connect to that. I can have an address connecting to my AWS cluster. So if I have an AWS running remotely, now I'm running my notebook locally, and everything I'm running over here is going to run distributed across that. So ray.init allows you to provide all these particular arguments. So this is auto would do that. I can actually define number of CPUs that I want, right? So if you do ray.init num CPUs 4, and if you have 12, it's only going to create 4 workers, each worker per CPU. So let's say you don't want to use all your 12 cores because you're running other applications. You just want Ray to reserve 4 CPUs, then it's going to allocate 4 CPUs or 4 workers. They will actually use that. If I have num GPUs, I can say, okay, use that one GPU for that. So these are kind of arguments that actually go to Ray init. I can define how much memory I want to use. I can define how big my shared memory you want to be, right? By default, there is a number, but you can actually define if you have large amount of shared memory that you can actually use. So these are all, I want to sync all the worker logs because each and every worker is running, it's logging that stuff. If you want to sync it to the driver, so you actually have some central place to run some log utility, or if you're using Splunk or using something else where you actually want to do searching and filtering, this is sort of a good way to do that. This is sort of more of a operational, people who actually are deploying those things have to worry about it. But if you wanted to run these things, you can actually do that. You can provide what we call runtime environments. So it's possible, for example, to say a particular task might need certain packages that don't exist on the cluster. So what you do is you create a runtime environment and you say pip install these are the packages I need for this particular task that I'm running. And it's going to do a pip install on the cluster for you for that particular task while it's running and not necessarily interfere with any other dependencies and when tasks are done. You do that. So you can actually have isolated runtime environments. All these are sort of part of this argument. I don't want to go too much into it because it's sort of more of an advanced class which takes a whole afternoon. So I have 2 sections. I have 6 modules. These are the 3 modules I cover normally during half day, and then there's another class in the evening. So just go through it, just read through it, and play around with it. These are some of the fault tolerance mechanisms that you can actually provide. So let's say you have a task that actually is a bit sensitive, and you want to say, if it fails for a certain reason, I want to have the maximum start 3 times, right? So that's sort of one way to do that. Or you might want to have a ceiling by say, the maximum way I want to restart is 5 times. After that, just give up. So those are the same kind of attributes, the characteristics and properties that you can assign to Ray actors. So there are a lot of code over here. You can actually also return. You can return a number of different arguments for a method, right? So if you actually have a function that returns a tuple or a function that actually returns more than one argument, you can just specify number of returns over here. In the class, you just specify method returns for, and you just return the method. So all these different ways you can program. So ray.method is more applied to a class. So for example, if I have a class over here that returns 3 method, I can use that. And it is invariably that you will have functions which are returning a tuple. You'll have methods which are returning something more than that, a dictionary or something else, or multiple dictionary. Ray put, again, these are all different arguments. You can actually put ray put and ray get. And some information you can actually fetch. Once you start a array cluster, you can find out how many GPUs you have, how many nodes you have in a cluster, array cluster, and all that. All those can be sort of provided through this array singleton object that has methods in it. And yeah, tonight you can probably start playing around with these things. So I didn't want to sort of go through it because this is a bit cumbersome, but I'll just very quickly go through this one over here. These are the command line arguments. So when you do array.init, it actually creates the cluster for you automatically. But what about if you don't want to do array.init? What about if you just want things run on the command line? So you can do array.start.head, and it's going to start that command line. And all arguments that you can actually provide in the array.init, you can actually do over here. So there's a huge list of array arguments you can actually provide. Array start help gives you all the different ports you can actually connect to, how many workers you want to have, if you want to connect to AWS cluster. These are sort of the arguments you provide. Number of CPUs, all that you provide in the array.init, you can do that on the command line. You can submit jobs to the array cluster you have started over here, right? So these are all these different CLI. You can find out what version it is. Array stat gives you all the statistics about that. Array start and stop obviously is self-explanatory. Array memory gives you the image of how your object store is running, what objects are running, what's the occupation rate and all that. Which objects are running, what the state of these are. So these are sort of commands. You can actually do array submit, right? So one way to do array submit job is do array start head, give your address to the local machine, and then use array submit job. And your submit.py will now run locally on the cluster, or it will run on a distributed manner. Okay, so I mean, this is all read-only stuff. I don't want to spend too much of time. This is the fun stuff for data scientists, those who actually are using Tune. Now, Tune is a very popular library. How many people are familiar with hyperparameter tuning or have used hyperparameter tuning to do that, right? One of the common sort of open source libraries is Optuna and Sigmod. All those are open source libraries. And you can actually use Optuna and you can use all this with RayTune, right? You can just specify all that. But RayTune also has its own, but it has all the algorithms which are actually supported. So if you actually want to have search algorithms that are open source, we make it part of the RayTune. If you wanted to use schedulers such as Asha scheduler, or if you're using halving algorithm to do that, or if you want to do early stopping, for example, you want to do that, you can actually do that. It's very cost efficient to use those with tuning because tuning takes a fair amount of time. If you have a large config space, tuning actually saves you quite a bit of time. And you want to make sure that you selectively choose the best search algorithm that gives you the most cost effective, because if you have GPUs and CPUs and if you use, let's say, grid search or you use random search, which is really a sequential way of doing things can get expensive. So there are strategies such as I use hyperparameter tuning with Asha algorithm, which will early stop sudden trials that don't do very well, and then continue on the ones that show promise, and it will only continue allocating resources and creating new trials for the ones which show actually particular promise. So all these are actually part of the RayTune. So if you're a data scientist and you're building a model and you want to start tuning those things, RayTune is actually a good friend of yours. And if you're using XGBoost, right? Now XGBoost is very, very popular. So the people probably die by XGBoost, both not physically, metaphorically speaking, but they love XGBoost. Good for tabular data. You can actually do register regression. You can do classification, all those things. But the problem with XGBoost, I wouldn't say problem, but it's limited in the words that on a single machine, you can use all the cores, right? It has the ability to say number of workers I want, and it will use all the cores. But you can't distribute over there, right? So we have what we call XGBoost ray replacement that takes the XGBoost now and then distributes that across the cluster. So you can actually use RayTune with XGBoost to distribute that. And this is the architecture. It's very simple. The 3 steps you actually need to do when you're tuning a particular model. One is that I want to define the search space that I'm going to give to my trainer. And then I'm going to use my search algorithms, and search algorithms could be any number of algorithms that Tune supports, which most of them are well known. And then I'm going to use a particular scheduler in conjunction with that. And then these combination will actually create the number of trials. And these trials are going to be distributed across each and every worker, and they will return the result, and I can actually finally analyze that result. Okay? So let's see how that actually works. Cool. Any questions? Brilliant. Okay. So this particular code is the way I've structured is that I'm learning everything local here. But if I wanted to make a choice, and if I had a cluster, I can actually just connect to my cluster just by saying ray.init. Here's my URL to the cluster, and I'm going to run everything across the cluster. The network connection over here is a bit dodgy, so I'm not going to try that. We'll run everything locally over here. Okay. So I'm just going to start that set to false. Initialize my my array cluster. So what I'm doing now is define my trainable function over here. I've sort of gone this a bit out of order, but first I'm going to define my trainer. And what I'm doing my trainer over here is I'm saying I want 4 actors, right? Do you remember the tree of pattern that we actually had? So I'm creating 4 workers here. I'm creating 4 actors who are going to do my trial. And I want to allocate 1 CPU per actor. So I have 4 workers, 4 actors are going to be created, and each of them is going to 1 CPU. I can use 2 CPUs if I want, but I can't. Or if I have a GPU that I'm training a ResNet model, or if I'm training a deep learning model and I want a GPU to do that, I can actually do that. And then over here, I'm creating my parameter, this particular class instant object called Hyperparams. And Hyperparams is a parameter you actually send to XGBoost saying, this is my parallelism that I want. I want 4 actors, 2 CPUs, and number of actors per CPU. So I'm defining my parallelism over here. And then this is my objective function, right? This is your objective function you would write for XGBoost, right? You write your training function that takes your training data, your checkpoint. The checkpoint directory is a directory where every trial we actually create a checkpoint to locate the parameters and to locate the model they actually created. So at any point you can actually go back and either restart from that particular checkpoint, or you can actually use that checkpoint if you feel that that's the best model that you actually got. Right, very simple. We're going to use your generic load breast cancer that actually returns my X value and Y value. One thing I'm done, if you were using XGBoost, you would actually use the D matrix, right? D matrix is the internal. How many of you use XGBoost? Okay, so those of you actually haven't used, I'll explain. D matrix is the internal data structure that is efficiently stores NumPy array. Over here, instead of using D matrix, because I want to distribute over that, I'm using Ray D matrix, right? What Ray matrix does, it actually takes that particular train, uses Ray data sets to distribute across my cluster. So if this was running on AWS, I would have partitions of data running on it, right? Or so I can train it on each and every different set of data. So that's my Ray matrix, which is a replacement for that. And then this is my training model for XGBoost. No different, exactly the same. I use the train. Parameters is my config space. We'll see what those parameters is. This is my config space that I'm defining. My train for XGBoost is train set. This is my evaluation result. I want the train set to use that. Verbose is going to false. The only difference the normal XGBoost and train XGBoost is this extra parameter that I'm indicating to Ray XGBoost as saying, use this for my parallelism. And then once I'm done with my checkpoint for each trial, I'm going to save that particular checkpoint as an XG model, and I'm going to go ahead and do that. So I define my training function. That was step number 2. Step number 1 in my diagram was define the config space, but over here I defined the step to out of order. So this is my config space, right? Same tuning parameters that you actually use for binary logistic. I'll have evaluation to be loss error. Now over here, I'm using tuning uniform way to have my space over here. And then these are just normal arguments to my config space, but instead I'm actually using the tune data structure to do that. So that's my config space, okay? And now, just to give you an idea, what actually happens is that when I start doing tune.run, what's going to happen is that each and every worker this particular orchestra will actually create a worker and launch my function to that. This is exactly the same pattern that we discussed when we were doing trio patterns. This is the trio pattern, right? So I've got my one worker over here, another worker process, the third worker process. All these, if I have X number of workers, those will actually have each worker that will have its own trial, that will compute its loss, and it'll compute its gradients, and then return the results back to the runner, and the runner will actually determine, do I kill this trial, right? Because I don't think it's very good. If I'm using Asha and I'm using early stopping, then you say, this trial is not making any sense, kill it. Take the next one in my config space, launch that. If that does well, continue with that, right? So that's what this does. And every time when the trial is done, it returns back the results back to the tuner, and the tuner will determine how to actually do the next trial. So here's my very simple argument. All I'm doing is tune, run the baby, right? Train function is the one, config is my space. This is the metrics that I want, error. I want to minimize the error, number of samples, which means 4 workers. And then these are my resources that I have. Run it, right? Now you can see actually it's actually running. And now you can actually see it's using Asha, doing checkpoint. What's going on over here? Now, this is actually going to the trial. You can actually see that it's created 4 ones. It used all my CPUs. It gave me, there's a checkpoint created. It actually terminated all the four models that I actually trained. Right? This just ran on my machine on 4 cores. But if I did that over a distributed cluster, you could actually see this running on 4 different nodes and then returning back the error. And then it's going to return me my best parameter. So this is my best parameter that I actually got. So all my config space that I had, it went through 4 different trials. It terminated one earlier because of the early stopping. And then it actually used the hyperparameter to do the distributed training. And then it find out this was my best hyperparameter, and that's what it is. This is my optimized tuning. So if I want to train this particular model, I just go to this particular directory, my checkpoint directory, and then get that particular trial, and now I have my best model, right? And then when you actually get back this analysis, this is just nothing a data frame, right? A pandas data frame that you can actually analyze, plot, whatever you want. And over here, I'm just getting the first 5 values. And you can actually see this sort of gives you the trial, how long it took, what are the parameters, all the good stuff, what was the depth, what was the number of trees, and so on and so forth. And my analysis in my log dir, that's where it is. And if I do an ls of the directory, this will actually have my best model in it. Any questions? 3 steps. Define your config space. Define your objective function, training function for XGBoost that you're going to use. Define your parallelism you want, right? 4 actors, 5 actors, number of CPUs you want per actor. What algorithm you want to use. By default, it actually uses Asha as a scheduler, right? But you can use, if I wanted to use search algorithm to use Optuna, I would be able to just define that Optuna. If I wanted to do something else, I can actually do that. But over here, it actually uses the Asha algorithm and goes head on with that. Any question? Good stuff, eh? Or you don't believe me? Just think it was magic.
I was trying it with the other 20 data sets. I still learned it was giving some error.
Oh, you got an error?
Yeah, well, I was trying it
Oh, iris, yeah, that's the next one. I think the next one is the next one. Yeah, I think the next one is the iris one. Let's find out if I get the same error. Okay, so homework. Obviously, I'm not going to ask you to do the exercises because not everybody's sort of familiar with some of, but this is actually a good blog. So if you really want to understand, hyperparameter tuning, what benefits it actually gives you, what search algorithms we support, there is a few examples over here that you can actually look at and then try some of these examples. It's very easy, cut and paste. I have a bunch of tutorials over here that I have links to. So these are, okay, I hope this link is not broken. I have a feeling it might be. Oh, brilliant, right? Yeah, so these are all the different search algorithms. These are all examples that tells you how to use it. These are all the trial schedulers that we support. Asha scheduler, right? That's the one by default. Hyperband, if you're actually using Hyperband, you can actually use that as well. Median stop, early stopping, all these are different schedulers which are part of Tune. And each and every of these actually shows you how to do that popular-based training. So if you're really a die-hard data scientist who actually lives and dies by squeezing every ounce of your model training using hyperparameter tuning, RayTune is your way to go there, right? Okay, the next thing I want to talk about is the Scikit-learn, right? Scikit-learn actually uses the same thing. Now, Scikit-learn actually has its built-in grid search and random search, but the problem with that is that those are not distributed, right? You can't use the cores and you can't distribute that. So we do have a replacement or drop-in replacement, just like we have a drop-in replacement for Ray, we have a drop-in replacement for Scikit-learn. And same idea, right? You create your model, you create your function, you create your config space, and then you just RayTune to tune your hyperparameter. So let's do the same thing we did over here. Go ahead and execute that. So now let's go ahead and create a random feature set, right? We're going to create a feature set of classification, 250,000 rows. Number of columns, features at 250. These are some other parameters you actually might want to use to compute that. Number of classes we're going to classify is 2, and then we just return X and Y, right? So this is a classification. We're going to create our classification data. Typical thing, we're going to create a parameter grid that we actually want with our hyperparameter tuning for HD classifier. So we're using Scholastic classifier over here. And now we're actually going to use the Ray Scikit-learn drop-in replacement we're actually using the tune. And we create this particular object called tune sklearn along with this. We're going to do early stopping over here. We're going to use all the 12 cores. If this was running on a cluster, I would say 40 cores, and we'd use all the 40 cores across. And now we're just going to do train. So let's just define this function and run it. So you can actually see starting using one CPU, you'll see actually numbers. It's now using 6. It's actually scheduling the trial. It's doing early stopping. Now it's dropped back to 1. It finished the trial. 1 running, 5 terminated. So this is 1 running and 5 terminated was something we actually did with our actor patterns. We were sending messages. This is how it actually sort of communicates back and forth. So this is still running. You got 1 CPU now. I don't have any GPUs running, so we're cool there. Let's look at what my dashboard is doing. It's going crazy. This is from the previous one. Okay, so all 6 were actually terminated. It took about 49 seconds to finish it. 250,000 entries to do the training. We did it across 12 of our clusters. This is my best tuning parameter that I got. Oh, why did I run it again? Silly me. Any questions over here? Yeah.
Yeah, so in that research CV initializer, you put HTTP classifier there. Can you put any sklearn pipeline there?
Yeah. You can actually have a pipeline run there, and it's going to do that. So anything you actually do in the sklearn, right, where you actually create a parameter, where you actually have a pre-processing unit and all that, yeah, you can actually do that. In fact, there's an example in that example link that I have that actually shows that you can actually use that. Yeah. Okay, we're done. So these are all the different examples that you can actually use with Tune. Yeah.
So if you want to use Hyperparameter instead of the random base search, would we have to import it from Ray currently?
Yeah. Yeah. Yeah.
It would be a similar class and we can pass it. Just want to.
Yeah, if you're using tune parameter, you have to import tune and then provide those uniformity using tune.that. So yeah, here are some examples you can actually try. There's a one on Scikit-learn adapters. A lot of examples for you to actually play around. There's so much stuff over here, I can't believe it. Okay, we have. Oh my God, I knew I was going to run out of time. Okay, modal serving. I think it would be unfair of me to let you guys go out without talking about Ray serve. Any questions before we actually move on? Those two examples were just to get your feet wet about, oh, we actually have Ray tune. I didn't even talk about Ray train, which allows you to do distributed training with PyTorch. But start with tune, and then RLib is a whole course of its own. Okay, so what are some of the challenges today of Ray serving, right? If you actually wanted to just, not challenges of Ray serving, but challenges of modal serving, right? You can use all these different kinds of frameworks, right? You can actually use Flask, you can use Fast API, which are actually good, that give you, they give you actually the web framework, and they're very easy to use, right? You just create an HTTP endpoint, you create a couple of decorators, and you write your particular modal, and you deploy it as a web application, and then you have an HTTP point, and you just make serialization calls to it. Or you can use custom tooling, which are very much specific towards these web serving frameworks, but they're a bit cumbersome because you actually have to start learning how these frameworks work and how this tooling works, how we deploy them, how we manage them, how we update them. All these actually have different configuration parameters, and you have to worry about managing, and becomes like an MLOps, not nightmare, but MLOps job for you to do. Then there is a specialized hardware, right? You got things like SageMaker, you got Vertex, you got Algorithmia. Those are sort of very specific, but they are kind of limited in terms of frameworks you actually want to use. What you really want, generically speaking, is that you want actually a framework that is agnostic. What I mean by agnostic is I can build a TensorFlow model, I can build an XGBoost model, I can build a Scikit-learn model, I can build a Hugging Face NLP or a Spark NLP or a Spark ML model. All those can actually be done because most of them have Python APIs. And so you actually won't have the ability for a data scientist or a machine learning programmer to take the best of the tools and use the best framework. And most of them actually have RESTful frameworks. So you want to be completely agnostic. You want to have the ability to use any of these. You obviously want it in pure Python, right? You want things to be very Pythonic. And you want not only to be able to use REST API to make the calls, but what about we actually want handles to the actual deployment, the code that actually was deployed, right? So you want to make sure those are Pythonic. Naturally, there's a marketing term, simple and scalable, but you also want things to be sort of working well with your CI/CD pattern. And last but not least, if you look at today how models are actually deployed at massive scale, models don't exist in isolation. They work in conjunction with a lot of things. So you might actually have a classifier, but the classifier might have other things that actually does before that. You might have an ensemble of models that actually take multiple models, then finally combine the output, and then send it to the final model. Or you might have a pipeline of an output, a pipeline of a model that you're actually building. So you might, let's say you have a pipeline of image classification. You're doing image classification that has a cat. Now, the first would be you identify it's a cat, right? Then you say, okay, I'm going to now pass it to my next model, which is going to do segmentation. So that model does a segmentation by identifying and putting boundaries around the cat, right? So that's going to be a separate model that actually does that. Then the output of that segmentation model might go to another model that says, I want to identify all the different items. So the cat is wearing a, wearing a bow tie. When was the last time you saw a cat wearing a bow tie? I don't remember. I've seen it, right? Cat wearing a bow tie or cat wearing a suit, because you might want to identify certain characteristics of the cat. So that's actually an image pipeline, right? It's done in parallel because one's output is dependent on the other one. You want to deploy them in a canary model. You want to deploy them in a rolling updates, right? Because you just want everything to be sort of updated right at once. So all these different things sort of require you to have a kind of a framework that allows you to support this different composite models. And RayServe happens to be one of that actually gives you the ability to do all this different model composition. And the TLDR basically is very simple. RayServe is scalable, it's very Pythonic. You actually get both the APIs to get the serve handles. Also, you also get the REST API. It's integrated fast API, so you can actually use fast API with it if you actually wanted to do that. And we support, or at least RayServe support, almost all the models that you can actually build with and deploy it. Now, you're not using RayServe to build things, you're actually using RayServe to deploy that. The architecture is very simple, right? You actually have an array instance which runs on top of array. And again, remember actors are all over the place, right? So we actually have a couple of actors. There's a controller, there's only one controller for the entire serve instance. There's a router that actually sort of takes your HTTP request, comes in, puts in the backend queue, and they are replicas. And replicas is how you actually scale things over, right? So replicas are your model deployment that allows requests to go in and do that. And then this is actually across the entire cluster, right? Each node has its HTTP request, and those actually get forwarded. And this allows us to do multiplexing or load balancing. Okay? High-level architecture, but I think it's important to actually have that. All right, so what happens in Ray, the reason I say it is Pythonic is that when you use a serve operator, such as serve deployment, two things happen on a function, right? Or two things happen in a class. When you define that particular serve deployment, it's going to translate that onto a Ray node that gives you the ability to actually access that as an HTTP protocol or HTTP handle, as a REST API endpoint, or it actually gives you a server handle where you can actually send a gRPC call to make a particular call, right? So I can actually use that using this, or I can actually just use this particular API to call it. So let's see how it actually looks like, right? Import serve. Now, remember, I don't have to start Ray init to do that. When I say server start, if there's an existing Ray instance running underneath, it's going to connect to that. So Ray instance over here is going to connect to the to an existing Ray instance. If not, it's going to go ahead and create one. All right, in my case, it actually created that, and now I actually have a cluster running. So let's see. Okay. So did you start? Cannot start. So if I go back over here and I look at my cluster, you'll actually see that I have a server controller. From the diagram, I have a server controller. I have an HTTP proxy. And if I go to my logical view, that actually tells me there's one of each actually created, right? Because I only have one server instance, so that's how it's created. Now let's go ahead and do our next thing. We're going to actually create a deployment. So first we're going to create a function. And just returns a hello. And to deploy that function, very simple. All I do is hello deploy. And now that has created one replica. And if I go to my cluster over here, you will see that I have a server controller. I should have one replica over here. And now I can just send requests to that particular endpoint, right? Just using HTTP, which was the diagram I showed you. When you do a deploy, it does two things for you, right? So here I'm just using request.get, and I'm just sending requests to it. Now let's do something else. Let's create a simple modal, which we're going to deploy that as a class. And then we'll do two things with that. We can actually use the HTTP handle to send a request, or we can use server API to do that. So your deployment can be callable, yes? Just in a class, you can define a particular class, you can actually make callable by implementing this dunder function. So I have a server deployment. I'm going to initialize with certain weight. I have a certain bias, and I have a certain prediction that I want. And since I want to have the ability to call in both ways, I'm just going to first find out where the callable was an instance of an HTTP request, or was it really a handle, right? So that's what this particular call does, or this particular if statement does, to check to see what instance of a request did I get, right? And I'm going to go ahead and deploy my particular server. Now I'm going to just go ahead and send the HTTP request to that using the some random data that I actually want. And all he does is just does some silly math to return me a prediction of that, right? So that does the prediction. I can actually list my deployments and find out how many deployments I have. So I have a hello function, and I have the ability to actually do that. So this is sort of very simple, right? I just created a particular class. My modal could be a very complicated modal over here. I could actually load a modal from a modal registry. If you're using things like, weight and biases, if you're using MLflow, your modal is actually sitting, I can actually load that modal in my instantiation and then just call the predict function. Very simple way, and the way you deploy it is just get that particular class and deploy it. Very simple. Any questions? Again, I didn't have to write any RPC call. I didn't have to worry about GCRPC. All that was very easily and quickly sort of deployed on my machine. These are all my actors which I actually created. Here's my replica. Yeah, I mean, you can put it behind, right? Because if you don't want to expose the HTTP, you can put it behind an nginx, right? So what you do is you get an endpoint. An endpoint is just any other endpoint that you can put it behind a load balancer. You can actually put, but the replicas is already being load balanced to you, right? So if you create 5 replicas and you're sending a request to all that, it will actually multitext across the replicas, right? But the initial request, if you actually wanted to, you can actually put it behind a reverse proxy, and then it will just forward that to the router, and the router will actually do the job. Any question? Okay. Very similar example, but slightly different, where we're actually using kind of 2 ways. I said, yeah, there are 2 ways you can actually access your endpoints. One is, the first example was just generic HTTP, right? But what about you want to use the APIs to get to that particular handle? So there are 2 ways to access that. One is getting an instance or handle to the actor itself from anywhere, or using HTTP, right? So that's sort of the diagram that actually that gives me. So over here, this particular notebook now, I'm just creating a particular modal, which is an instance of a modal that is very generic. I'm creating a class. And again, very same argument. If I get a request to HTTP, I want to get the query parameters for my payload. Or if it's just a request from the handle, I just want to get the right data and just do the prediction on the particular modal that I have. Now, as I said, this particular model can be loaded from anywhere, right? If you actually train, let's say in our previous example, we trained our XGBoost model and we took that over checkpoint and we put it in our S3 bucket, or we registered with MLflow, or we registered with SageMaker, or we registered with weight and biases. And over here, I can just use the weight and biases to get that particular version of the model. So now I have that particular model in that, right? Because model is nothing but just some weights which are defined, serialized weight, right? Some language models are huge, but this is where you can actually initialize the model. So this is a way you can actually have an existing model that you can actually make that part of the deployment and then deploy it. And you have a choice to say, okay, I want 5 replicas, I want 2 replicas, I want 3 replicas, I want GPUs to do the prediction. If you had multiple, for example, if you have multiple models that actually does a composition, then you can actually have your pipeline built right here, right? So over here, we'll actually see that I think it's the next example where we actually do the pipelining thing. Okay, so I do a server start. And now I'm showing you, I'm doing something slightly different, right? I'm providing deployment options, and I'm providing the name of a particular deployment so I can identify those, right? And I'm saying the number of replicas that I want to, and this is where the models are deployed, right? This is where the models are. So if I had my pickle model sitting somewhere in S3 bucket, just go ahead and read that. So this is what this particular thing does. And let's list of deployments. Okay, now we're going to try to get the access to the deployment using the first method, using serve handle. I'm not doing HTTP request here, right? I know my replica names are, because I need that to identify. It has to be unique, right? So deployment name had the name associated with that. I get the handle by saying serve get deployment handle name, and they get the handle, right? That just returns me now an instance of that particular handle. And then with that handle, I can just call the remote function. Simple as that. Right? I don't have to make an HTTP request. I just make remote with some random number that's going to do the prediction for me. Whereas if I did HTTP, I would actually have to say a get or a put. But over here, I can actually do a remote handle. This is a good way, for example, to do pipelining, right? So if I have 3 models that have to run in sequential, I can get handle of each of those. So I get the input of the first one, I do a prediction, I get the output of the first model, I send it to the second one, I get the third one, and then finally I send it to the 5th one. That's sort of a good way to use this strategy to do pipelining. So notice that it's actually multiplexed between I had 2 replicas. Remember, there's a different PID. So I have rep 2 went to a different PID, rep 2 request went to a different PID, rep 1 request. So these are 2 I've created 4 replicas, 2 for each. And when I'm sending a request, you can actually see that it's multiplexing between those 2, right? And you didn't have to worry about that. You didn't have to create the infrastructure to do that. The deployment of RayServe does that. The architecture that actually defines how it actually does that, all that is actually done for you. And so if you had a complicated model, you actually see a lot of output. But the illustration over here is to give you an intuition that using RayServe, we can actually create those deployments. You can access them in multiple different ways. You can use replicas to scale it. And you can actually define, in that options, I could have defined, I want GPU for this particular replica, or I want a partial GPU, or I want a fraction of a GPU, right? So if I have a Hugging Face that I'm doing sentiment analysis, I think the last notebook actually shows you how to do that. You can use this particular strategy to do that. Okay. Now I'm going to do the same thing using HTTP, right? Over here, I'm just sending the same parameters. Over there, I did a .remote call to call the handles. Now I'm just using the HTTP, and the output is the same. Again, I'm getting multiplexing. And then we do a ray shutdown. Okay, so we're not going to do the exercise because we don't have time. We only have 20 minutes left. But try to play around with different kinds of requests and try to change the model or trying to change the number of replicas, and you actually see. Try to change it to 4, and then send, I think I have 20, so send over 80 requests, and you would actually see things evenly distributed across. Okay, so this is actually an end-to-end example. We won't go over through this, but what I wanted to actually show you was this composition model, right? This is this particular example where I'm using ensemble, right? I have two different models. Each gets a prediction, and then its output actually goes to the final model to the prediction. So what we're doing over here is we're actually doing some sentiment analysis using Hugging Face. So I got the model. I don't even have to build this model. I'm just logging it directly from Hugging Face. I'm tokenizing it. And I'm going to make a prediction of a tweet. Oh my God, Elon Musk is buying Twitter. We are effed. You know what I mean? So how does Hugging Face analyze that, right? So it's not part of the requirement, so we need to do pip install transforms in Torch. If you don't have that, go ahead and install it. And this is Hugging Face Transformers that allows me to do all these kinds of sentiment analysis. I can actually use GP3 model to finish my text for me, right? So if I type something. But this is just taking particular text that might be coming from a tweet API to do that in real time. So let's go ahead and do that. I already installed it. We shouldn't do that. Okay, so I'm going to import the necessary libraries that I want, or the libraries modules that I want from the Hugging Face transformer. I got text classification, auto tokenizer, and then let's create some fake tweaks that we actually have. And these tweets right now, even though they're coming from a list, this could be actually a streaming tweet coming in a real-time application that you're getting it from handle or hashtag python.com. Wish we'd actually done that. These are live tweets coming up. And you can actually do some sentiment analysis on that aspects of it. So we're going to go ahead and create this particular tweet. And then fetch tweet is just random tweet that's going to pick this up, right? So we have a fresh tweet that's going to come in, just a function that does that. And now I'm going to create two deployments, right? I'm going to create the first deployment, which is my sentiment model. And my sentiment model wasn't the one that I trained. I'm using a pre-trained Hugging Face model to make that as part of my first deployment, right? And so I have my tokenizer, I have my pipeline that I'm saying, use this particular tweet-end model, use all the tweets, but all the text that you've learned from distilled BERT and all uncased fine-tuning using English. I'm going to do the sentiment analysis, and once I'm done, give me the sentiment analysis of that particular label to see whether it's a positive or a negative tweet, and assign the probability of the score, how accurate it is. My second function is translate. So I'm going to take the tweet that actually came in that was positive, and now I'm going to pass that over to a translator that's going to take my English tweet that I have and translate it into French. Right? So that's the second one. Now I'm going to create my composed model. This is composition, right? This is a very common pattern that you actually will build if you're deploying models where you have multiple models that are deployed together as one deployment. And the main model that's actually deploying is a composite of a couple of models. So my composition model in my initializer, I create this instance, and I'm using the get handle. And the reason I'm using sync as fault is because I want to do this asynchronously. And the reason I want to do asynchronous is because I want to be able to scale it, right? Because my requests are going to be coming at massive, so I want to just run this in the background asynchronously. And it uses async IO to be able to do that. So it just returns right away, and then in the background it's running in the event loop. And as soon as that event is fired, boom, it's going to get your value back, right? So this is my init call. This is my async call. I'm defining that as an async call. I get the request. And the first thing I'm going to do is I'm going to send it to this particular model. And I have two await calls. One await is for the sentiment model. The reason I'm using await is because this one is going to go ahead and return me an object reference. Right? So I had to wait for the object reference to finish, right? Because it's going to do a put. The second await is going to wait for that to finish to get that particular value. I'm not doing I'm not doing ray.get. All that is actually done automatically for me, right? So I get my sentiment score as a value, and then I send that to the data to whatever data I want to the second model, and that returns me text. Then I combine the output to return back to me to where we actually want. So that's my sentiment analysis. So that's the object reference that's going to return, and then I'm going to start, right? So this is going to start a particular array cluster, and we'll create these deployments, right? The first thing, I'm going to create a sentiment model, followed by translate model, followed by composite model, right? What I've done is I've created a composition of these 3 models that work in tandem rather than, oh, I'm going to send a request over here and I'm going to wait. All these actually done in one deployment. And then let's send some data to it, right? Now, this could be, web applications that actually is getting from a Twitter handle API directly from either hashtag or from some user who is doing sentiment analysis on the tweet coming during election or doing a World Cup football or doing PyCon, whatever. And that's going to now send a request to my composite model. What happened over here? Okay. So I get my sensitive, positive, and then it's translated into French. And let's go to the next one, translate into French. Anybody speak French over here, Lucas? Did you translate? Did you do a good job? Look at the English text and look at what it converted into. It's all right. Oh, it says 99, 96%. It's not my, it's Hugging Face, don't blame me. Yeah, but it actually does a decent job. I mean, if you didn't want to do it, you could do this synchronously, right? I just did it asynchronously because I think in production or in real-time situation, you want things to be the low latency. But if you make it synchronous, it might take a while. So asynchronously is a lot faster. So this is all happening, But if you look at it, there's not much code here. Literally, there isn't that much of code. I'm pretty much reusing, much of the trained model, and I'm just wrapping it around RayServe, and I'm using any one of the design patterns or ML platform patterns to deploy it. It's pretty easy to use. And if you actually wanted to try this at home by taking the GP2 model and transform Hugging Face into spaces, very easy to do. All you replace is the translation model with the GPT model that actually does the completion or task, and then send this particular tweet. It will add extra text for you. You don't have to do the sentiment analysis. You can just do the GPT 3, I believe, or is it 2?
2 is underneath.
Yeah, 2. 2 is 3 is not yet, but 2 allows you to do text completion.
They never released. You can look at GPT EO something or GPTJ something.
Yeah, so I think we're done. So I mean, I didn't have any exercises of it because I think it'd be fun to do that. But try using some of your models. Use this particular design pattern. See which is easier. Is it HTTP easier for you, or is it serve handle? I like the ability to actually get a handle, because then I know exactly the code I'm executing, or Python code. And this actually, the example is there that actually shows you how Fast API is integrated with that, right? So you just create the handle of the Fast API, and then you can actually create all these different routes. You can create all these different routes for get and put. So if you have multiple routes that you actually want to create with Fast API, you can actually do that. And Fast APIs is very much integrated with that. I do have another tutorial. It's called, well, if you go to Academy, Anyscale Academy, you will see in there. I show how you can actually use Fast API to do that, and how you can actually use the. Yeah, try it. I mean, you should be able to actually replace that with Fast API. You know what I'll do? Maybe this afternoon I'll change it to Fast API and upload it, and then you guys can actually see it. So I think we're almost 10 minutes. Are there any last-minute questions? I know I threw a lot of stuff at you. I apologize if I really put you guys to sleep, but I hope that this class was helpful, was useful. And there's a lot of material with you, so you can actually take it with you. And you have my contact information, right? I mean, I would love to keep in touch. Where's my slides? The slides are here. PyCon US. Yeah, just DM me on Twitter. Follow me, I'll follow you. I know it sounds dodgy, but you can do that. If you just want to send an email, just send email at jules@anyscale.com. I think I have it at the end. And yes, I am on Slack all the time, 24/7, live there. Yeah, join our meetup. Yeah, here's my contact info, it's on the slide. Feel free to contact me. Send a connect to LinkedIn, just tell me you're in the class. Love to keep in touch. So I hope you do all the homework exercises, and thanks a lot for your 3.5 hours of time with you. So good. Oh, I got to do one thing. Selfie, guys, selfie. I can't do this. I cannot go home without having a selfie. Come on, man. All right, guys. At the count of 3, Ray rocks. Woo! Lovely. You guys are just a wonderful audience. I wish I had more stickers for all of you. Hold on.